Okay, hello, welcome back to another lecture for COP-3402. I'm Brent, and today we're going to be discussing system calls, or Syscalls for short. So by the end of this lecture, you should have a good understanding of what system calls are, how they're used, the basics of how they work, and some of the benefits the kernel provides as an abstraction for interacting with your hardware. I want to begin this lecture properly by retracing our steps a little bit back to the first lecture of this course, and where we had defined system software itself. So we had defined system software as the bridge between the kernel and applications, and this diagram illustrates that idea. Applications reside at the top of this diagram, so these are things like video editing software, internet browsers, audio streaming services, and at the bottom there's the hardware. So you have things like CPUs, motherboards, memory devices, and graphics cards, RAM sticks. And even within these categories of hardware, there is more diversity. So there's different kinds of CPUs. There's Intel CPUs, there are AMD CPUs, there are ARM CPUs. For GPUs, there are NVIDIA GPUs, there are AMD GPUs there as well. For memory, there's all different kinds of memory, right? There's like SSDs, hard drives, flash drives, and even within SSDs there's even more variety now. We have NVMe drives, we have SATA drives. And as a programmer, you do not want to have to deal with the intricacies of how all these different pieces of hardware work, because every kind of hardware has different specifications and timing requirements for how you are supposed to send data to it and read data from it. And that's one of the things the kernel provides as a benefit is abstraction, virtualizing the hardware for you. When the kernel provides really an abstraction for you to just write to any piece of hardware and consider that as working. The kernel provides built-in functionality for writing to all these different pieces of hardware, reading from them, and you as a programmer don't need to worry about when you go to save your code in your text editor that you're saving to a flash drive versus a solid-state drive. So that's one of the benefits of the kernel. Another is that it allows you to share hardware resources, and this is both memory and time. So if you have like one RAM stick and you're running multiple programs on your computer, the programs don't have to compete for that same area of RAM. The operating system, the kernel, will divide up the RAM appropriately for all those different programs to run. And in terms of time, you might have like 10 different programs running in your machine, and your machine might only have one CPU. And a lot of machine consumer products these days have multiple CPUs, but we'll say you only have one. Even if you only have one CPU and you're running 10 different programs, the scheduler that's part of the operating system and part of the kernel will schedule these programs to run on the CPU at different times, so they each have their own fair access to running on the CPU until they finish. And this is known as like time splitting. That's one term for it, or time sharing. Sometimes you'll see that in like textbooks. The final benefit that the CPU provides, the kernel provides by this virtualization, is protection of hardware from users. So, for instance, if you're on a server, like we have the grading server for this course, or not the grading server, but Eustace, the server where you're submitting your projects, writing your projects in this course. It would be bad if a user could directly interact with the hardware on Eustace's on Eustace and actually read and enable the user to read another student's homework assignments, submissions, or exercise submissions, I should say, or even worse, modify another user's code so that they get a bad grade. The kernel protects against this. It prevents users from accessing other users' data. Additionally, the kernel virtualizes applications while they're running, their memory spaces, which disallows your C program from reading memory that it shouldn't, or from crashing and then breaking other parts of your computer in the process, or even let's say you have a memory leak in your C code and your C program crashes. The kernel will ensure that leaked memory gets released back to the operating system and the rest of your hardware. It prevents that leaked memory from being permanently gone from your operating system. And this leads us to the idea of a kernel user space boundary. And I have a diagram here to illustrate this. So what might seem to be the case when you are writing, when you want to write to a file, let's say, it might seem like what's happening is that you're making a write command, and you're writing to, let's say, your hard drive here. I'm going to make it a dashed line. So let's say you're writing to your hard drive from user space, like in a user application, like you're in your text editor and you're pressing Control-S and you're saving your file to a hard drive. You might think you're going directly to that hard drive. Your file contents are going directly to the hard drive. But this is not what's happening. I'm going to draw a red X here to signify this. Instead, what's really happening is that you can imagine that the kernel has these sorts of black boxes inside it, with functionality for writing to specific kinds of hardware. So when you make a call to write, and let's say you want to write to a hard drive, the kernel will handle the writing for you and make sure that the write succeeds for that hard drive. And if you wanted to also write to a flash drive instead, let's say, you could do the same operation. There's still only one connection between user space to kernel space here, that write command. But the kernel will handle the details to make sure that you're correctly writing to that USB drive. So the kernel, again, abstracts away the details of how writing works. And other operations too, like reading, for instance. And what's cool about this is that if you wanted to, if you had like a new device you wanted to add support for to your kernel, you could do that. You could add like another, let's say, black box here, and then add support for some other new device, new and exciting device that you want to add, some kind of sensor or something like that. And these black boxes are really, well, additional black boxes that do not come with the kernel. They're called drivers. So drivers you can think of as just like regions of code that are added to the kernel for supporting new pieces of hardware. And a lot of work in the Linux kernel, if you go on like the Linux kernel source code, you go on GitHub and look at it, or go on the Linux kernel website for looking at its source code. There's different mirrors of this as well. You can see that a lot of the Linux kernel's code is driver code for supporting new devices. It used to be the case, like years ago, that Linux could not support many drivers, and so it was not practical to use as a user operating system. But nowadays, there's so many, the kernel supports so many drivers that it's actually practical. So much for this diagram here. Now the way that you can actually interact with the kernel and take advantage of all these nice abstractions is through a interface called Syscalls. So again, if the kernel contains all the abstractions for writing to files and whatnot, as programmers, the way we interact with the kernel, the API that the kernel exposes to us are these Syscalls. So yeah, some examples are inter-process interaction, memory, reading and writing memory, manipulating files, getting information about files, etc. These are functions that the kernel provides that you can call within your C code, or really at the basic level, syscalls are assembly code, which when called tell the kernel to interact with specific pieces of hardware in specific ways. So I have a diagram here to better illustrate this, I think. I'm going to zoom it in now. When you call, well, in your C code, you can call a syscall. So for example, we have here some C code on this top left corner, and it's calling this syscall execve. Don't worry about what this is, what this does. We'll go over that in a later lecture. But for now, just know that this is a syscall in C. And really, it's actually a wrapper around a syscall. So this will call, when you call this syscall here, it will run the glibc wrapper function for execve. Now, glibc is the GNU implementation of the C standard library. So this comes with most C compilers. So when you call execve, the execve syscall wrapper function will run. It will do some things like copying arguments into appropriate register values, copying the number that identifies the syscall in assembly code to an appropriate register, the EAX register specifically. And then the important thing it will do here is raise an interrupt. This is a specific kind of interrupt known as a trap. And what the trap does is signals the trap handler, which is a mechanism in the kernel itself, to go into kernel mode and execute a syscall. Which syscall? Well, it reads the number that was passed via registers, the EAX register, from the glibc wrapper function. So in the wrapper function here, we're passing the __nr_execve syscall code. And I think on ARM machines that's 11. On 64, x86 64 machines, I think that's 57, if I'm not mistaken. And what will happen is the assembly code here in the trap handler will jump to the appropriate function in this syscall table, the appropriate syscall, and execute it. And this syscall is implemented in the kernel as a system call service routine. So this is like the C implementation of that function. And you don't have access to the C code on your own Linux machine because it's already been compiled and built. But this source code that as a developer would see it for the Linux kernel would be like this. And what happened here, so the trap handler would index into this table, call the syscall at the appropriate index. We would go to the system call service routine in the kernel itself, run that service routine to completion. Control would return to the trap handler would finish executing. Control would go back to user space, back to the glibc wrapper function. That would finish executing, and then your C code itself would continue executing as before. So as you can see, there's like some steps to making a syscall from C code, because we're not directly making syscalls in assembly, we're making it in C code. And so there is like, because of all these steps, there's actually a bit of an overhead associated with making syscalls from within C code. It's not that large, but it is appreciable. Like, you should be aware of it. If you're trying to write super optimized C code, you want to reduce the number of syscalls you make because of this overhead. But for this course, it doesn't really matter. Just a bit of a fun fact if you're trying to optimize your C code. And to go back maybe to the previous slide here, the reason why we have system software is so that users don't have to just write assembly code all the time to make use of syscalls. That's one of the reasons, really. That's why that's why like a compiler is an example of system software, because it lets you define a higher level language like C or Python for making more ergonomic providing more ergonomic ways to make syscalls instead of just writing assembly code all the time to interact with your hardware. And this is a bit of a mistake here. I need to fix this in this slide. This is not a hardware interrupt. I believe it's a software interrupt because you're making this syscall from within software. And the specific kind of interrupt is a trap. Hardware interrupts actually come from like hardware devices like Ethernet cables and whatnot. When they read data in, or if they're disconnected, they send hardware interrupts. So now on to syscalls proper. How can you access them from C code? Well, they look just like C functions, but there are certain conventions they follow that we're going to talk about later in this lecture. So, especially around returning error values. And you can check at any time what syscalls are available. I'm going to go to a new tab here by running man syscalls. And you'll see there's a whole page, and it tells you the system call is the fundamental interface between an application and the Linux kernel. So this is what we've been saying this whole lecture. And it tells you here, I'm just going to read this because it is very informative. System calls are generally not invoked directly, but rather via wrapper functions in glibc. So just like we saw in that diagram, glibc, or perhaps some other library. Often the glibc wrapper function is quite thin, doing little work other than copying arguments to the right registers before invoking the system call, and then setting error no appropriately after the system call has returned. So we're going to look at error no in a little bit, but for now, this should all track with what we saw in that diagram. The syscalls you're making or invoking in C code are really just thin wrapper functions that copy some values to registers and then execute the syscall in assembly and then in the kernel itself. So I'm going to quit this, go back to the slides here. And you'll notice in the man syscalls page, if I scroll down, there's a whole list of all the syscalls available to users. There's a ton of them. And you'll notice that next to each of these, there is a number here. This specifies the man page section that these syscalls belong to. Now, what is a section? Well, if we go at the man pages, look at the man pages for man itself, kind of meta, but let's try it. the man pages for man describe 9 different sections of the man pages. Section 1 is for executable programs like ls or cat. Section 2 is for syscalls, provided by the kernel. And section 3 is for library calls. These are functions that, like malloc or fprintf, that are not system calls. They're not thin wrapper functions. They do a little bit more than just wrap around syscalls that are built into the kernel. So for some examples, let's look at man for open, and you can actually just run man fopen, and there's no ambiguity here, so man can actually tell that you want to look at the library call, because there's only a library call named fopen. There's nothing else called fopen on my machine. And the man page is to actually tell you like what the function returns, what arguments it accepts, etc. And there's man pages, library pages for other functions like printf, fscanf, etc. But if we go to man2, we can actually access the man pages for syscalls. So here's an example of where you want to specify the section number for a man page. So if I were to just type in man open, you'll notice that it opens the man pages for section 1 of the user manual for open. This is not the same thing as the syscall for open. This is an executable function or executable command called open. Instead, I want to access the syscall, so I would type in man2 open. And this gives me the syscall information for open. You can see the return value, the arguments, etc., and the header that it comes from. And there's other syscalls here, write, read, and notice that these are analogous to these library calls, fopen, fprintf, fscanf, open, write, read. These library calls are, you can think of them almost like thick wrappers around syscalls. They provide more than just basic functionality, they provide some additional functionality. So in the case of fopen, we get a file pointer as a return type, which is a bit nicer to work with than a file descriptor, which we'll be describing shortly. fprintf, you get, and fscanf, you get formatting. You can use format strings to specify the kind of data you're expecting to read in. With read and write, you're really just writing bytes. Like if I open up the man pages for open again here, you can see that, sorry, not for open, let me look at the man pages for write. You can see that its arguments are just like byte arrays essentially, and you even have to specify the count, the number of bytes you want to write. So it's a lot lower level. And now on to error handling. So because we're in C, and we're not in a language like C++, which has like try, catch, and exceptions, or Java or C# even, we're in C, we have to do all this error handling ourselves. And the way that error handling works with syscalls is, honestly, I kind of hate it, but it makes sense because it's very simple why they implemented it this way, is you just call the syscall and then check the return value. So I'm going to give an example now of what this looks like. I have a file here called, let me actually clean up what I have in this directory here. I have 2 files that we're going to be looking at, 2 C files, open_complete and open_simple.c. If I also have a make file here, so I'll just cat out the contents of the make file for you to see. The make file just has some rules for generating binaries from open_simple and open_complete. So I'm gonna not go over that anymore. We've already reviewed make files. Just know that I've put this here as a convenience for compiling these files. Now if I open open_simple.c, I'm going to step through this line by line. Actually, and let me change this line here to the one from the from this first example, so we can get some better intuition of what's going on in this code. Here we're defining a main function. That should be no surprise. You should be familiar with this from your introductory C programming courses. We're defining a constant char array called path. We're defining it to some file called somefile.txt. Note that this file does not exist in my current working directory. So if I were to type in ls here in vim, you can see that there's no file in my current directory called somefile.txt. And then we're calling open here, we're making a call to the open syscall, and we're passing to it a path and a flag called oReadOnly. So let me open a new window here to show you what this means. Let me, actually I'll just open the man pages in vim. Man2 open. Open expects the path name, so the path to a file, and it says here in the description, open system call opens the file specified by path name. And it accepts some flags as well. And the mode argument is only useful if you're going to be creating a file. We're not doing that, so we don't need to pass the mode argument. And what happens here is that if mode succeeds, it returns a positive value, which is a file descriptor. And a file descriptor, you can think of it conceptually as an ID number mapping to an inode number. So remember from one of our previous lectures, inodes are like the ID numbers that the kernel assigns to files when they are created. And a directory is nothing but a mapping from file names to their inode numbers. Well, each program has its own, also has a mapping that maps these file descriptors to inodes, essentially. So you can think of it like an inode almost. It's not quite an inode. It's going to be different from an inode, but you can think of it like we have access to like a way of identifying files. That's a number. It's an ID for a file. That's not an inode, but it's like an ID for a file. That's all you can think of as file descriptors as. But if open returns a failure, if it fails, then it returns a negative 1. And then the convention with syscalls is that if a syscall fails, it places its failure value, the specific kind of failure that occurred, in the global variable errno, which you can only obtain from this errno.h header. And if you want to see all the different kinds of errors that are available, I'm going to open the man pages for open again here. You can press / and then type in errors in all caps, and it will take you to the part of the man pages for that syscall, which describe all the different errors. And these are all macros, so you can actually write these values directly in your C code and check for what kind of error occurred. You'd have to compare this against errno to check the actual error. Another one that's useful to check for when looking at these syscall man pages is the return value, because it tells you what happens. So it says on success, open and friends, return the new file descriptor, a non-negative integer. On error, -1 is returned, and errno is set to indicate the error. So this is what we were talking about, what I said earlier. So anyway, let's see what happens here. So if -1 is returned from open failed, we print out an error message. We use a format string here with the format specifier %d to print out the exact value of errno. And then we exit with exit failure, and then finally return 0 to indicate success. So if I were to run this, I'll just quit this here. And actually I'm going to open tmux so I can have 2 windows open at once. If I were to make open simple and then run open simple, we get the message open failed with error 2. Well, that's not very informative. And what does 2 even mean? Well, remember, let me open the open simple file again so I can show this, demonstrate this. This file, somefile.txt, does not exist. And if we go to the man pages for open, there's actually an error number here called enoent. It says ocreate is not set, and the named file does not exist. So we're opening the file for read-only here, but the file does not exist. And we can assume, or we should assume based off of this error message here, let me quit this and run open simple again with error 2, that enoent actually has the value 2. But we shouldn't have to know this information. Like this is like a magic number that we shouldn't just have to know off the top of our heads. Do you really expect someone to know all the different values of all these different error messages for every single syscall? No, that would be ridiculous. So what we have instead is a helper function called perror. And if I go to the man pages for perror, it's actually a library call, not a syscall. We can see that it says the perror function produces a message on standard error describing the last error encountered during a call to a system or library function. So what that means is that in our example here, opensimple.c, we can replace this call to fprintf with perror. And the convention is to pass the name of the function that raised the error. So we'll say open, I'll save this, and in this window I'll make the open simple binary again. I'll run it, and now we can see we get the error message open. So what this perror call here will do is prefix the message with whatever you pass in the string. So we have the prefix open here. Open, no such file or directory. So now instead of some like arcane, esoteric magic number, we get a nice error message telling us exactly what happened. So this is much more desirable. Now let's look at a more complete example of using Arno. So I'm going to open this other file here, open complete. And this one, let's walk through it. Now we have a main function that accepts two arguments, argc and argv. So this will be the number of arguments passed to the program on the command line. This will be the actual arguments themselves. And by convention, argv0 always contains the name of the program that we called. So if the user passed an argument to this program, the count of arguments should be at least 2, because the name of the program itself will count as 1, and then the argument that the user passed will count as the second one. But if the user passed fewer than 2 arguments, so fewer than 1 argument really, we'll print a usage message to standard error along with the name of the program. So let's try that. So if I were to make open complete here and then try and run that binary with no arguments, we get the usage string open complete file. It tells us what we should do to call this program correctly. Otherwise, we're going to extract the argument the user passed, argv1, and store it in this variable called path. Then we're going to call open. We're going to open the file at that path in read-only mode and restore the result in fd to store the file descriptor that we get from doing that. And if open failed, then fd will be -1, so we'll print an error message and then exit. Otherwise, if open succeeds, we're going to then try to close the file descriptor using the close syscall. So if I open this in Vim, you can see it. It's another syscall. And if close fails, we'll print out that close failed, again exit 1, and then if nothing else goes wrong, we'll print success. This is actually pretty common, this style of writing very straight line code where you're just checking return values and then exiting on failure. Pretty common when you're writing syscalls, you'll be writing code like this. It's pretty frequent. It gets kind of boring almost, which is a good thing. If you're writing code and it's just boring to write it, that's probably good because it means that you're not going to run into any errors. All right, so let me try making open complete. I think I don't need to remake it, but I'll make it again. Okay, yeah, we're good. So I'll try running this again, and I'm going to pass a file that does not exist to it this time. So we'll just say foo.txt, this file does not exist. And we get the nice error message, no such file or directory. But if I pass something that does exist, like maybe the source code to open complete itself, kind of meta, but we'll try that, we get the string success. So we successfully opened the file, and then we successfully closed the file, and then printed the exit string, the string success. And I forgot to put the exit 0 here, but actually the C standard specifies that the main function is unique in that if you forget to put a return value, the compiler should automatically insert a return 0 at the end of it. So we should be fine. And that actually wraps up all I wanted to talk about today. In the next lecture, we'll be talking about using syscalls to access file information. Specifically, we're going to be using the stat syscall. That's going to be more complex than the open syscall, so be prepared for that.